All right, so we're reviewing for probability, and we're picking up kind of where we left off last time. And this is combinations. Combinations are where order doesn't matter. What are the P ones called? Permutations, and then the order does matter. Okay, on pizza it doesn't matter because, you know, you're just putting this, I don't care if the cheese goes on top or if cheese goes underneath the you know, like the other ingredients like sausage or whatever. So the order doesn't matter. So I use the C. And I was just saying before we started recording here that you probably want to, ooh, it's a buzzing noise. You probably want to set this so that you can do it in your head. You want to set this into, make this into a big fraction. So what we're going to do is have you practice right now. I'm going to switch to the next screen in a second here once I power that down. There. I want to remind you how these work. I'm going to do one with you, and then I'm going to have you do one by yourself. What you're really doing with the combination is making a big fraction like this, and then on top it's 6 factorial. Does that ring a bell? And then on the bottom it's the 6 minus the 2 factorial. And then the C's are different than the P's, only in this way. The P formula is exactly the same. 6 factorial over 6 minus 2 factorial. But one of these has an extra thing in it. Do you remember which one it is? The combination has an extra thing. Where? On denominator. It's in denominator. And what is that extra thing in this case? 2 factorial. Is it always a 2 factorial? No, it's whatever's here. If that is a 3, then it'd be a 3 factorial here. Okay, now why? I want you to understand why. I hope if I were to die tomorrow that one thing you'd remember about me is that I really wanted you to understand why, where it came from, not just to be able to do the shortcut. So this compared to this, just think about it in the real world. Which one should be bigger? The P or the C? The P should be bigger because why? Because the order matters. And so if I was taking little groups of 2, that's what this 2 means, is like little groups of 2, then I have my group of 2, and then if it's like Bob and Sarah, but then if the order matters, then I also have to count it Sarah and then Bob. So then it's twice as many things to have. Okay, so this one's supposed to be bigger. And then this one is getting smaller by dividing by something. Okay? Remember that? Now, and actually, when we're doing these, we need to know what these mean. 6 factorial means 6 times 5 times 4 times 3, 2 times 1. All over 6 minus 2 factorial is 4 factorial, which is 4, 3, 2, 1. And then I can cancel. You remember that? All right. Then see if you can do these. By hand, no calculator. I'll pause while you do that. That is the correct way to set it up. Then you'd have 4 times 3 times 2 times 1 over 3 times 2 times 1. Cancels. The answer's 4. Raise your hand if you had that one right. Good. Next one. Same idea, except it's simpler. 4 factorial over 4 minus 3 is 1 factorial, so that's just 4 factorial, because 1 factorial is equal to 1. 4, 3, 2, 1. 4 times 2 is 12, times 2 is 24. Final answer, 24. Raise your hand if you had that one right. Good. Notice, it is not always just twice as big. Look it, it's 6 times as big this time. Why? Why? Yes. So it divided by 6 there. You're right, because 3 factorial is really 6. So it divided by 6. So why? Why? Because in the real world, you'd have these groups of how many? You have these groups of 3 people. And then if you have to count what order they're in, then there'd be 6 different ways to arrange each group. All right. Moving on. Already talked about that stuff. Here we go. Trees. Trees are incredibly powerful when it comes to probabilities because even though they're a pain to make, they are good at solving pretty much any probability problem. I've got a simple but big tree that I want you to make. And it's going to take an entire side of a sheet of paper. So find me that. Back side of what you're on or whatever. And I'd like you to make me a tree. Very comprehensive. That's the whole heads tails type tree. Okay, coin flip. And it's going to be 4 separate times. So remember, the first time is like where you go like this. That's your first one, heads, tails. And your second flip is like this one, heads, tails, heads, tails. And your third one and your fourth one. And at the end, it's really important to me that you have the summary thing, like heads, 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 heads. The next one will be heads, 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 tails. Make all of those. I know there's a bunch. I'm going to pause while you complete your chart. Right. Okay, there we have it. We've made our tree. If you're not done with yours, just keep cranking it out because you'll need it for the questions I'm going to ask you in a minute. Okay, it's always important to go back to what does probability really mean. It's the things that you want divided by the things that are possible. What if I told you that I wanted the tails, 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 tails scenario? I wanted all 4 tails. Well then, I just have to follow down that branch. Tails, 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 tails. I get to the bottom, and that means that I had done 0.5 times 0.5 times 0.5 times 0.5. It's 0.0625. That's it. I just have to find that branch, and I'm done. I've got my probability. But I thought probabilities were always divided by something. They're always what you want over the top of what's possible. Why don't I have to do that? Because what's possible is a total of 1, exactly. All the things were possible. Everything on this list was possible. So if I add everything on this list up, it all adds up to 1 whole. So it's really 0.0625 divided by 1. Right, I'm trying to just buy some time here for some of you guys to finish your last few things. You don't have to keep writing all the decimals on there because why? Same thing on all of them. They're all 0.5s being multiplied. So this is a really pretty simple tree. Like I said, it's simple, but it's big. All right. Now, here's a typical question you could be asked about this tree. In fact, I'm going to give you 3 questions about this tree. The first one is, find the probability of 3. Now, I'm going to say exactly because this can be confusing sometimes, whether I mean at least or at most or exactly 3 tails. Probability of exactly 3 tails. I know most of you guys right now turned back to your chart and you're looking for things that are exactly 3 tails. I'm going to put little stars by the ones that are exactly 3 tails. This one has exactly 3 tails. This one has 3 tails. This one has 3 tails. I think there's one more. There it is. This one has 3 tails. So is the answer 4? If the question was just how many ways can you get 3 tails, the answer would be 4. But if the question is what's the probability of getting exactly 3 tails, I take these guys, add them all up, and divide by all the things that were possible, which is 1. And so I just basically add them all up. So 0.0625 plus 0.0665, is there a faster way? 0.0625 times 4 would be faster. All right, next kind of question. This is kind of medium hard. What if I said probability of 3 or more tails? What does that do that's different? All right, we'll continue this in the next part of the video.